Hello there, Mr. Sutton here with the AB Calculus 4-5 Extra Practice Number 1 Solutions on Points of Inflection. For this problem, we're given the graph of f of x on an interval from 2 to 7. We want to know how many points of inflection this graph has on the interval. A point of inflection happens whenever the concavity changes from concave up to concave down or vice versa. So concavity changes directions how many times here? Well, we start off concave up, and then somewhere around here we're going concave down. So we've got 1 point of inflection right here. We're concave down for a while, and then somewhere in here we're going concave up again. And we're concave up until we get somewhere around here, then we're concave down, and we're concave down the rest of the way. So that's going to be 3 of those. Choice C. For this problem, we're given f with a second derivative given by f double prime equals this stuff here. We want the x-coordinates of points of inflection for f. So on this one, note that they already gave you f double prime, which is what you need to do sign analysis on to figure out points of inflection. So we're just going to take what they gave us, f double prime, set that equal to 0, find our critical values, and use our number line. So we see that f double prime of x equals 0 if x is 0, 3, or 6. Putting those on a number line, critical values, and this is an f double prime line now, so we have 0, 3, and 6. Testing something in each interval, so let's see, to the left of 0, let's try -1. Now this x squared is always going to come out positive no matter what, so it's really these two parentheses that are going to determine our sign. So we've got, let's see, a negative and a negative if I plug in -1, so that's positive overall. And then between 0 and 3, we've got 1. That's going to give us a negative times a negative again, so positive still. Between 3 and 6, we've got 4. That's going to now be a positive times a negative, so negative. And bigger than 6, we've got, well, let's just do 7. So positive, positive comes out positive. So I see here that f double prime changes sign at x equals 3 and 6. Therefore, f has points of inflection at x equals 3 and 6, which is going to end up giving us choice D. For this problem, we want the equation of the line tangent to y equals x cubed plus 3x squared plus 2 at its point of inflection. So this is a multi-step problem. We have to first find the point of inflection, and then we have to write a tangent line for it. So to get the point of inflection, let me start by figuring out what the second derivative of this thing is and finding critical values for that and doing some sign analysis. So I'm going to label this as f of x from here on out, just so I can refer to it quickly. So let me first find f prime of x. I'll be using that later anyway when I want the slope of my tangent line. That's going to be 3x squared plus 6x, and then that 2 is just gone, that's 0. And now let me go one more derivative. F prime is going to be 6x plus 6. Setting that equal to 0, I see that I have a critical value at, let's see, -6 divided by 6 is -1. So let me go on my number line now and see if that actually is a point of inflection. I mean, it's the only one that we have, so it probably works, but always better be on the safe side if you have time. So f double prime number line, here's -1. Plugging in something less than -1, let me try -2. Plugging that in the f double prime here, that's going to be a -12 plus 6, which is negative. And now something bigger than -1, how about 0? That'll be 0 plus 6, which is positive. So I see here that f double prime does change signs at x equals -1. So big surprise here, f has a point of inflection at x equals -1. Now that I've found that, let me go ahead and write the tangent line there. In general, I'm going to use point slope, y minus y1 equals m times x minus x1. Specifically, I need my x1 here is this -1 I just found. So y1 is going to be f of -1. M is going to be f prime of -1. And then I still have, this is going to be x plus 1 if we do minus minus. So let me fill in these values. F of -1, if I plug -1 into the original function, well, let's see here. That's going to be -1 plus 3, which is 2, plus another 2 is 4. And then f prime of -1, well, here's my f prime formula here. Plugging -1 in there, that's going to be 3 times 1, which is 3, minus 6, so -3 for that, so equals -3. And then we still have x plus 1. Now, I said multi-step. We're not done yet, believe it or not. That doesn't match any of the answer choices. They're all in slope-intercept form. So we're going to go back and convert this into y equals mx plus b form. I can do that by distributing this negative 3. So this would be negative 3x and then minus 1. But we're going to add the 4 from over here. So that actually ends up being actually, it would be negative 3x minus 3. But then if I add the 4 over there, it'll be a negative 3x plus 1 when we simplify. So this is going to match answer choice. Let's see. Does it match any of the answer choices? Yes, answer choice B. Whew, better after all that work, right? On this problem, we want to know at what x value the graph of 1 over x squared plus 1 over x cubed has a point of inflection. So we need the second derivative of y and then some critical values to help us test this out. Let me start by rewriting this as x to the negative 2 minus x to the negative 3, just to make it a little easier to take those derivatives. And I need to get y prime before I can get y double prime. So this is going to be y prime equaling negative 2x to the negative 3 plus 3x to the negative 4. All right, let me go ahead and take one more derivative now. So y double prime, that's going to be 6x to the negative 4. And then we'll have minus 12x to the negative 5. Now, in order to get some critical values, it's going to be easier, since these are actually really fractions in disguise, it'll be easier if I merge this into a single fraction. Let me rewrite these as fractions. So 6 over x to the 4th minus 12 over x to the 5th. And then turning these into the same fraction, I can do that if I get a common denominator of x to the 5th. I'm almost there. This x to the 4th needs to get multiplied by an x, as does the 6 up here. So when the dust settles, then I'll have 6x minus 12 all over x to the 5th. And I want to figure out where this equals 0 or is undefined. 6x minus 12, the numerator, is going to be 0, which will zero out the whole fraction, if x equals 2. And now I see that if I plug in 0 for x, f double prime, or actually y double prime, is going to be non-existent at x equals 0. So that's another critical value that we may need to test on our number line. Let's go ahead and do that now. So I've got 0 and 2. Plugging in some numbers, less than 0, we've got negative 1. And then let's see here. This is our simplified y double prime right here, this fraction. So let's use this. So that's going to give me a negative numerator, negative denominator, positive overall. Now something between 0 and 2, how about positive 1? So that's going to be negative numerator, positive denominator, overall negative. And then finally, we've got something bigger than 2, like 3. Numerator and denominator both positive, so overall positive result. Okay, so I notice that I'm changing the sign of y double prime at 0 and 2. 0 is a little bit special, though, because if you plug 0 into the original, it comes out undefined. Because y of 0 does not exist, we would say there is no point of inflection at x equals 0, because, quite simply, there's no point at x equals 0. Let's try the other one then. We've got a sign change at x equals 2 in y double prime. That means that y then, because if you plug in 2, you get something that is defined, that means that y is going to have a point of inflection at x equals 2. So that's going to be choice C. For this problem, we're given the derivative of f prime right here, and we want to know how many points of inflection f has on the interval negative 2 to 2. One way you could do this is to figure out f double prime, which is going to be kind of gnarly and involve a product rule, and then see where it crosses the x-axis. Alternatively, we could just graph f prime the way it is and see how many times it turns around, because mins and maxes for f prime are really points of inflection for f double prime. All right, so we can say then that f prime changes from increasing to decreasing or decreasing to increasing at how many places? It's grapher time. So here's my y equals on my calculator. I am just literally plugging in f prime there. And for my window, I'm going to use the interval they gave us of negative 2 to 2. So go to window, and we'll do negative 2 for x min, 2 for x max, zoom 0, and that's going to give us this beautiful picture. Kind of looks like the McDonald's logo a little bit. But see, the important thing is here, if we count up how many times we're changing increasing to decreasing or vice versa. We've got 1, 2, 3, 4, 5 times. Therefore, f has 5 points of inflection on the open interval from -2 to 2. So choice E. On this problem, we're given a table of f double prime for some polynomial, and we want to know which statement must be true. So the first two statements are talking about f increasing or decreasing, and that's really not what this table is going to help us with. F double prime tells you the concavity. It tells you whether the rate of increase or decrease is itself increasing or decreasing. But since we don't know what f prime actually is, whether it's positive or negative, knowing whether f prime is increasing or decreasing, which is what these will tell us, is not going to help us out here. So in general, we don't know enough about f prime. We don't know the sign of f prime, so we can't pick either of these answer choices. We just don't have enough information. Next one, f has a local max at x equals 1. Well, for this we would need to know, since it's a polynomial, we would need to know that f prime of 1 was 0. We don't know that, so this is also a no. All we know is that f double prime of 1 is 0. So that all that means is we have a possible point of inflection there. Don't really know much else. Now this next one is a little bit trickier to disprove. Graph of f has a point of inflection at x equals 1. This is a tempting choice because point of inflection is going to happen first off where f double prime is 0. So right away you're thinking, well, this could be a point of inflection. And second, we need a sign change in f double prime before and after the candidate here. Well, before we have a positive. After this, -7 is negative, so you might look at this table and say, hey, we're changing positive to negative, therefore point of inflection at 1. But although we know that we're definitely hitting the x-axis with f double prime when we get here, we're touching the x-axis, we don't know that we're actually going through it at this spot. We could, so we don't know we're crossing at that spot, we could actually be bouncing off of the x-axis here, which would give you an output of 0 for f double prime, bouncing off the x-axis, going up, coming back down, and then crossing later on. So we don't have enough information to say that this is the point of inflection. We know there's some point of inflection between here and here because at some point we change positive to negative. We just don't know that it's right exactly here. Last option, graph of f changes concavity in the interval 0 to 2. Now this we can prove, and the way we're going to do it, the original function is a polynomial. That means when you take the derivative, its derivative is a polynomial. F prime is a polynomial. The derivative of a polynomial f prime is going to be a polynomial f double prime. We know that f double prime is a polynomial, which means it is continuous, which means that I have to, so this last one was no, just to finish that thought. So that means that since we have a polynomial which is continuous, I have to go through all of the f double prime values between 5 and -7 to get from here to here, which means I've got to go through 0 for f double prime somewhere in between the x values 0 and 2. So because of this, f double prime must change sign on 0 to 2. This is basically IVT, intermediate value theorem. So we can actually prove this one. This is true. This is a yes. Choice E. On this free response problem, we're given f is a continuous second derivative, or has a continuous second derivative for all x. F of 0 is 2, f prime of 0 is -3, and f double prime of 0 is 0. So they give us all this information at x equals 0. G is a function whose derivative is given by g prime equals all this crazy stuff that involves the function f. We'll deal with that when we have to deal with it, I guess. Part A, first part, we want to write an equation of a line tangent to the graph of f when x equals 0. So in general, I'm going to use point slope, y minus y1 equals m times x minus x1. This is always a good starting place when you need a tangent line. So x1 in this case is going to be the x value 0, and then y1 is going to be f of that, f of 0. M is going to be f prime of 0, the slope at 0. So that we have that times x minus 0. Let me go ahead and fill in some values now. And they actually gave us everything we needed. So we have y minus 2, because that's what they said f of 0 was, equals f prime of 0, so -3, times x minus 0, I guess you could leave it that way, and we've got our tangent line. Bam! For this next part, they're asking, is there sufficient information to determine whether or not the graph of f has a point of inflection when x equals 0. Explain your answer. So already this is kind of suspicious, because if there is a point of inflection, they generally just say, hey, go find it. Here they're asking if we can even find it. So taking a look here at why there might be a point of inflection at x equals 0, we're talking about one of two things. You can either talk about where f double prime changes sign, or where f prime is changing increasing to decreasing. We definitely don't have increasing, decreasing information about f prime. All we know is f prime of 0. F double prime of 0 is at least 0. So there's at least a possibility that we have a point of inflection here, if it's 0 or undefined. However, we don't know whether the sign of f double prime actually changes before and after 0. Because we don't know whether f prime changes sign at x equals 0, maybe it's positive, then positive, or negative, then negative. Because we don't know that, we don't know enough to say whether or not we have a point of inflection there. On this part, we're given that g of 0 is 4, and we want the equation of a tangent line for g at x equals 0. All right, so let me use point slope again on this one. So y minus y1, in this case that's going to be y minus g of 0, the y value at the x value of tangency, equals, well, now we need m, which is going to be g prime of 0, all that times x minus 0. We already know g of 0 is 4, so we don't have to find that. But we do need to figure out g prime of 0. So that's going to use this crazy thing up here. We're going to have e to the negative 2 times 0 times 3 times f of 0 plus 2 times f prime of 0. All of that, I'll put that in the brackets. Cleaning this up a little bit, we have, this is e to the 0, which is just 1. In here, this is 3 times f of 0. F of 0 is 2. 3 times that then is going to be 6. Here we have 2 times f prime of 0. Well, they said f prime of 0 was negative 3. 2 times that is minus 6. And if we look closely here, we've basically got 1 times 6 minus 6, which is 0. So plugging it all in, we have y minus 4, that was our g of 0 value, equals 0, that was g prime of 0, times x minus 0, which is great, kind of useless. So this is actually our tangent line. You could leave it like this in this form, or if you really wanted to, you could zero everything out on the right side and add 4 to get the horizontal line y equals 4. For the final boss battle on this free response, they want us to show that g double prime equals all this stuff. And then, does g have a local max, min, or whatever? Does g have a local max, just local max, at x equals 0? Yes or no, and why? Okay, so first, to get g double prime, we start with g prime and take the derivative, and that's going to require the product rule. So let me go ahead and use my product rule here, u prime v plus uv prime. So setting up the box and ribbon, I've got e to the negative 2x, and here this is going to be 3f of x plus 2f prime of x. Derivatives now, e to the negative 2x, that's going to be negative 2 e to the negative 2x. And then this will be 3f prime of x plus 2f double prime of x. So not too nasty there. And now it gets nasty. When I multiply all this stuff out, I'm going to have a whole bunch of terms, and I have to turn it into this right here. I'm just going to multiply everything out and distribute right away. That way I don't have to do it later, and I can just collect things, cancel things, hopefully. Let's do this. So we've got, using our ribbon now, negative 2 e to the negative 2x times 3f of x. That's going to be, I'll simplify as we go, negative 6 e to the negative 2x f of x. Next, we've got this term times 2f prime of x. That's going to be negative 4 e to the negative 2x f prime of x. Going back the other way, we've got, let's see, this will be 3 e to the negative 2x times f prime of x. And finally, we're going to have 2 e to the negative 2x f double prime of x. Can I clean this up at all? Well, one thing I notice is that we've got some like terms here. We have an e to the negative 2x f prime, e to the negative 2x f prime. So these two terms can be combined to just give me negative 1 e to the negative 2x f prime. No other like terms anywhere else, This is just an f of x. This is an f double prime of x. Can't combine those. I also noticed that I can factor out some things. Like, for example, I could factor out an e to the negative 2x. That would leave me with negative 6f of x. And we said that we can combine these terms, so there was just a negative one of these left over. So that would leave me with a negative f prime of x then if I take an e to the 2x, negative 2x out of that middle term. And then this last one, this is going to be just like 2 f double prime of x. And what were we supposed to prove that this thing looked like? Oh, well, we got it actually. Nice. All right, so now that we actually matched what they had up there, we have to answer the question, does g have a local max at x equals 0? Now, the key on this one is recognizing that we have perfect information about this function at x equals 0, and we know nothing about this function anywhere else. I mean, we've defined g in terms of f, and that's great, but f, we don't know anything except these 3 values here that they've given us. Otherwise, f could be doing anything other than the fact that it's continuous here. So what we're going to do is use the second derivative test. In order to do that, I have to first show that g prime of 0 equals 0. Well, when did I find g prime of 0? I know it's been a while since we did part C of this problem, but we actually found g prime of 0 there. We had to in order to find the slope of the tangent line for g. Back there, we said that g prime of 0 equaled 0 when you simplified everything. So there it is again. So we have a critical value for g at x equals 0. Now we have to plug 0 into the second derivative and see if that comes out positive or negative. So if I do that, plugging it in here, that's going to be, let's see, e to the 0, which is just going to be 1. And then we're going to have negative 6 times f of 0. Well, negative 6 times 2 is going to be negative 12. Now we're subtracting f prime of 0, so subtracting negative 3, so adding 3. And then finally we're doing 2 times f double prime of 0. Well, f double prime of 0 was 0, so that's just going to be 0 for that last term. So we have 1 times negative 12 plus 3, which is negative 9. And that's going to be our final answer on this one. Well, no, that's our final concavity answer. G double prime of 0 is negative 9. Now, to get the final answer as to whether we have a local max or not, we notice that negative prime is a negative value. That means that G double prime, and you don't have to write this out, but G double prime is concave down at x equals 0. If we're concave down and we're at f, and the first derivative is 0, that means you're at the top of the frown, that smooth turnaround at the top of that concave down interval. So this is going to give you a local max at x equals 0 using the second derivative test.